Thank you for joining me for the latest installment of the Brookhaven Instruments Learning Corner series. Let me take a minute to introduce myself. I am Daniel Seaman. I am a senior scientist at Brookhaven Instruments. And today we're going to be talking about dynamic light scattering, and more specifically, how we could use DLS in order to improve the quality of otherwise difficult measurements, including biological samples such as proteins and biopolymers. When you're making a DLS measurement, what do you actually want to get out of this? You want to be able to measure size, right, because you're using a particle sizer. You want to be able to measure the size of your protein monomer. In this case, we're looking at bovine serum albumin, which has a molecular weight, or a monomer molecular weight, of around 66.5 kilodaltons. So we want to be able to put a sample into the instrument. We want to be able to measure its size. And we want to be able to use that information to tell us, is this sample, is this monomeric? Are we looking at monomer, dimer? Are we looking at aggregated protein, or a submixture? This is what you want to get out of an experiment. Unfortunately, it's often more complicated than that. Don't worry, we're definitely going to come back to this, but what information do you really want to get out of this measurement? You want to know size, and you want to know if your protein is aggregated. And you have to dig through all this to get at it. Okay, so don't worry, we're going to come back to this. We're going to make sense out of this. Why are we interested in monoclonal antibodies? So where does this interest come from? So it's one of the fastest growing classes of pharmaceutically active biologics. So we're talking about really is monoclonal antibodies. They're synthetic recombinant proteins produced in cell culture. And what are they used for? They're used for immunoassays. So the most common type of immunoassay that a lot of people are familiar with is the ELISA, or the enzyme-linked immunosubstrate assay. There's a number of other rapid diagnostic kits. It's used in vaccine research. And then there are also the primary number of well-known injectable protein drugs are all monoclonals, anything that ends in mAb. These are usually drugs that have to be prepared at very high concentrations. It has to be stable. These are extremely expensive to manufacture. They rely on some of the most expensive bioprocessing apparatuses, ultrafiltration, depth filtration, protein A chromatography, various different chromatographic polishing steps, validation. This is a very expensive process, and quality control failures can be extremely costly. So we're going to be talking about data that was collected on a Brookhaven Instruments BI200SM research goniometer, pictured on the right. So this is a multi-angle light scattering instrument. The main components are a laser, a goniometer base, and a detector. The detector could be a photomultiplier tube, or it could be an APD. It really doesn't matter. It's just a method for acquiring signal. This is not our only dynamic light scattering instrument. We also have a benchtop instrument, the NanoBrook, with similar capabilities. So when you're making a DLS measurement, just as you can see by convention, large angles, so typically those greater than about 120 degrees, are referred to as backscatter, or backscatter angles, means large angles. Right angle refers to an angle of 90 degrees. That one's somewhat self-explanatory. Forward scatter typically refers to very small angles, usually those under 45 degrees. So we notice that this angle dependence gets absorbed in this Q term. This Q vector incorporates a number of constants, including the wavelength of the laser and the refractive index of the solvent. That's where that comes in. So what's the source of our signal? So when you're making a dynamic light scattering measurement, what you're really measuring is motion, specifically Brownian motion. So we're looking at large particles that move slowly. Look on the right, we see for a small protein, it's rapid motion. So rapid motion means rapid fluctuations, or rapid photopulses. We autocorrelate the signal. We get what we call an autocorrelation function. And then we can see that this decay is related to a diffusion coefficient, and then that is itself going to depend on the angle-dependent term that we defined on the previous slide. So as you can see, this gamma is the decay constant of the autocorrelation function. So just to summarize, large effective hydrodynamic sizes, so large diameter means slow diffusion, small diameter means fast diffusion. So slow and fast modes. Slow and fast really just refers to the magnitude of the diffusion coefficient, and that diffusion coefficient is directly reciprocal to protein size. Okay, so our first case study, and bear with me, we're definitely going to get to monoclonal antibodies, but not to keep you waiting too long. We're going to go into serum albumin, so it's a fairly conventional serum protein. It's often used as a surrogate for more expensive pharmaceutical proteins in proof of concept experiments. So again, remember what we really want to get out of this measurement is the size. So we see we drop serum albumin into a DLS instrument, we get an effective hydrodynamic size of 7.5 nanometers, which makes sense. 7.5 nanometers for a roughly 66.5 kilodalton protein. This makes intuitive sense. In mind, everything is relative, of course, but I would consider serum albumin as a medium-sized protein. This is a very reasonable hydrodynamic diameter, and it matches what you would expect for bovine serum albumin monomer. And we're working in conditions where we don't expect to see BSA dimer. So one thing to keep in mind, effective diameter, depending on exactly what literature you're looking at, people either report radius or diameter. You go to make a measurement of a protein and it's twice the size you're expecting. Don't panic, just go and check if your small d is a small d or a small r. Right, so remember to always compare diameter to diameter, radius to radius. Right, so where does this angle dependence come in?
Note the axes. So if we look at the y-axis, we see decay rate, or gamma, units of inverse seconds. If we look at the x-axis, we see our q vector squared, so units of centimeters squared, reciprocal.
Here I'm showing data collected at effective scattering angles of 30 degrees, 45 degrees, 90 degrees, 135, and 150. So if we make a measurement at a single angle, of course we can measure a size. You can see there's this relationship between this gamma or decay rate that you're measuring and your q vector, which gives you a diffusion coefficient that directly gives you a size. And so it should make intuitive sense that although this rate depends linearly on q squared, the diffusion coefficient and the size should be invariant. I don't expect to put a sample in, measure it using backscatter, and get a completely different size than if I measure at 90 degrees. Right, that wouldn't make intuitive sense to me as an experimentalist, and I suspect wouldn't make sense to any of you either. So you can see we're looking at basically this linear dependence. In order to do this type of analysis, you really want to have at minimum 4 or 5 scattering angles. Remember, on benchtop instruments, you're dealing with 3 fixed measurement angles and a goniometer. You can sample a near infinite continuum of scattering angles, although you don't need to do that, of course. But for this statistically, you probably want to have at least 4 or 5 scattering angles. So we note, because this is linear, we would expect to measure the exact same size at every single one of these scattering angles. So a nice linear slope gives us a diffusion coefficient, gives us a size, and more importantly, it gives us the same size at every scattering angle. Fortunately, it's not quite that simple. So if we look at our lowest angles, so we look at our forward scatter angles, our low Q angles, now highlighted, we see that we actually deviate from this linear relationship. Our decay rate just looks a little bit too slow, our average decay rate looks a little bit too slow. Why is that? Well, back to this finally. So we notice, so just to orient yourself, you're going from left to right. The leftmost correlation function, highlighted in blue, is 150 degrees, and we step through, it's 150, 135, 90 degrees, 45 degrees, and 30 degrees. So what's the first thing that we notice? We notice that it's shifting rightward, which makes sense, as per the previous slide. For the size to be constant, this correlation function has to shift rightward as we change angle. But then what is the thing that actually jumps out at us? Well, that we have this second decay that becomes apparent when we get below about 45 degrees. So you would never know that this was here at 90 degrees or higher, but that it becomes very obvious that there's some small amount of aggregate that's present. Because we have this sort of forward scatter intensity bias for large particles, we really only start to see it at the lowest angles. We can't measure the size of a protein aggregate, but we're able to detect, on a number basis, very small concentrations of aggregated protein mixed in with a dominantly monomeric sample. This will be very useful if you want to make an aggregation detector, less useful if you want to measure the size of small particles. As long as we're careful of how we set up this experiment, and we pick sensible scattering angles to measure at, so let's say 90 degrees or higher, we're able to measure the size of bovine serum albumin monomer fairly easily. We get a sensible answer. We get an answer that makes sense based on our knowledge of the sample and our understanding of the technique, and we just have to be more careful as we approach forward scatter angles. Well, let's move on to the more interesting case, where interesting does sometimes mean complicated, but we're going to find a way to deal with that. Now we're finally talking about antibodies. Okay? Antibodies are important, which I'm sure you already agree, otherwise you wouldn't be watching this video. So you sat through 8 minutes of me talking about serum albumin, so let's talk about antibodies. Again, why is this important? Because they're used in immunoassays, rapid diagnostics, vaccines, and injectable protein drugs. So almost every major pharmaceutical company has some sort of mAb-based drug in their pipeline or already on market, and they're some of the single most profitable biological drugs on the market presently, and quality control failures are super expensive, and you're always going to be dealing with regulatory concerns. Now that I've reminded you why we care about mAbs. Alright, so as we saw for BSA, you can easily take a simple sample and make it more complicated than it needs to be. So let's take a complicated sample and make it simple to measure. So how are we going to do that? As we already saw, the scattering angle that we select definitely matters. Right? I wouldn't want to pick, based on what we've learned so far, I wouldn't want to pick a forward scatter angle to measure the size of a monoclonal antibody. So we know we're going to want to be at 90 degrees or higher, so let's just start with a scattering angle of 90 degrees. So theta equals 90 degrees, we're at a right angle to the laser. Look at our monoclonal antibody. Okay, so we pick a single theta, which means that we're measuring at a single Q. We're really just measuring one point on this line. We're potentially expecting a mixture of different sizes, so we want to pay attention to the ranges of measurable decay rates. So we want to pick a sensible correlator layout. So on our research instruments, and the same correlators underlie both our research instruments, our research goniometer, and our benchtop instruments, you have a very high degree of correlator control. So we separate data acquisition into high, low, and mid-speed circuits. So as you probably remember me saying, small proteins, they move very rapidly, which means you need high-speed data. Aggregates move very slowly, so you need low-speed data. We're no longer concerned with angle dependence because we're just measuring at a single angle. So we can do that. We measure one correlation function for a stable, monomeric, monoclonal antibody, no aggregation, no chemical degradation, there's no disulfide scrambling, perfectly happy monoclonal antibody measured at a single angle. We get a single effective hydrodynamic size, so the little d sub h is an effective hydrodynamic diameter. We get 12 nanometers, which is consistent with the dimensions of the protein, or the effective dimensions of the protein. Remember, mAbs are kind of big and floppy proteins. They're not quite as compact and globular as a lot of other conventional proteins. So 12 nanometers diameter, and we can see that we're able to measure the size of this one thing that's present in solution. We have a nice stable mAb, we measure it, scattering angle of 90 degrees, we get a reasonable size. Right? So here we use rapid acidification in order to induce producing conditions where the sample is chemically stressed and where we would expect rapid aggregation of this antibody. So what do we see? The first thing we see that it's an average. Okay, so if we're looking at this correlation function, we ascribe an average diameter to it. It's much greater than 12 nanometers. Much greater than 12 nanometers. And that's because, as you can see, looking at this isn't a single exponential function anymore, because there's more than one thing present. So of course the average is no longer meaningful. What do we do here? We deconvolute this into a multimodal size distribution. We see protein aggregate, so we look at the two peaks, or debatably two peaks above 500 nanometers. Those might not really be discrete species, they might be. We definitely see that aggregate is present. We're not that interested in measuring the size of a protein aggregate. It's well above the size of our protein monomer. So what do? So we look at our protein monomer, which is still resolvable. So we note that even in the presence of this heavily aggregated protein, we're still able to see what remains of the free protein monomer. And notice that as a basis, just as a percentage of total signal, the dominant peak here is actually aggregate, and a relatively small fraction of your signal is coming from protein monomer. So how well do we actually do at measuring the size of unaggregated protein in the presence of large aggregates? So the answer is we actually do pretty well. Again, we get a hydrodynamic diameter of 12 nanometers for our antibody monomer, our mAb monomer, and then we see our aggregate peaks are substantially larger. Notice that our decay rates are orders of magnitude apart. And okay, so we're able to actually resolve all of these, and we can accurately measure the size of a small protein monomer, even though the majority of our signal is actually coming from the aggregated protein. So as I mentioned before, why does this work? It works because we were very careful when we picked a scattering angle and a correlator layout. So our correlator layout gives us temporal resolution, so as you see on the y-axis on this plot. Our correlator layout tells us what, and correlator layout both means the range of decay rates that you can measure, but it also means how closely spaced they are. So it's not just smallest and fastest delay, it's also the spacing, right? So it's a mixture of both resolution and also measurement window in sort of time domain. So we see that we're able to resolve these three peaks, these three modes. So if we look at our fast mode, our mAb monomer at 90 degrees, we see that it's perfectly resolvable from our two aggregate peaks. It's debatable whether the aggregate peaks can be resolved from one another. It's not necessary. If you're satisfied to know that it exists, then this is more than enough information. We see that if we wanted the maximum resolvability of all of these different species, we'd want to go to the highest angle possible, so we want to go to backscatter. And if we really want to emphasize the existence of aggregate, or if we want to be, as we saw earlier, sensitive to the existence of aggregated protein, even at small number concentration, we would want to go to forward scatter. But we wouldn't really be able to expect to be able to adequately resolve, say, monomer, dimer, trimer, aggregate, etc. In other words, forward scatter is not going to be terribly useful for measuring individual sizes or resolving them from one another. Alright, so just a quick recap. So selecting an optimal scattering angle is going to be key to making an accurate measurement of challenging samples, especially biological samples, heterogeneous samples. Angle-dependent measurements can be informative, especially when starting with unknown mixtures. So as we saw, we use a goniometer to do continuous angle dependence. We could measure as many angles as we want, but this is almost never necessary for a typical size measurement. So if you have a single, stable, homogeneous, monodispersed sample, usually one scattering angle is more than sufficient to accurately measure a size. So key points here: low angles are very sensitive to larger particles. So if you wanted to make an aggregation detector, you'd want it using a forward scatter angle. But they're not terribly helpful. Forward scatter isn't terribly helpful for making an accurate measurement of the size of multiple species that might be coexisting. So a mixture of, say, aggregated protein and free protein, forward scatter would not be your go-to angle. Backscatter is very well suited for resolving mixtures of monomeric and aggregated protein, so just generally, as long as you're above about 90 degrees, this will work fairly well. In summary, right, so protein aggregates can become gigantic. They can easily reach large sizes on the order of hundreds of nanometers or larger even meaning microns. This can easily complicate an already challenging measurement. But just because it's complicated doesn't mean we can't simplify it. This principle with a pharmaceutically relevant protein, monoclonal antibody, pharmaceutical grade mAb, and we're studying it in both monomeric and aggregated state. And so despite the fact that this aggregated sample is extremely heterogeneous, we're able to still obtain useful information from this experiment by carefully selecting both the correlator layout and the scattering angle, and so we're able to fully resolve the signal from monomeric mAb that happens to be coexisting with that of aggregated protein. So thank you for your time, and if you want to learn more, definitely feel free to contact us either at info@brookhaveninstruments.com, or if you want to subscribe to our Learning Corner series, you feel free to contact us at learningcorner@brookhaveninstruments.com. Thank you.